Today we are going to go over the second part of 8.4, the limit comparison test. So yesterday we learned the direct comparison test. We should find a new series to compare with the original one. If the bigger one converges, the smaller one converges. If the smaller one diverges, the bigger one will diverge. So today we are going to learn the limit comparison test. Let's have a look. Given two series an and bn are both positive, as n go to infinity, if the ratio between an and bn give us a number, then we can say series an and bn, they both converge or diverge. They have the same property. And if the limit of the ratio is 0 or infinity, then the test is inconclusive. We have to use another test. Our job here is trying to find another series and then take the ratio. There's a general rule. How do we find a new series to do the limit comparison? We only keep the highest powers of n in the numerator or the denominator. So what does that mean? For example, given the series n cubed plus 1 over 5n to the 5th plus 2, how do we find another series to compare with this one? We look at this one, the highest power of the numerator and the highest power of the denominator. So these are the two terms. So this series is what we are going to compare. 1 over n squared, we are going to compare this one with the original series. Let me show you some examples. So the basic idea is, in order to study the original series, convergence or divergence, we compare an to a new series, bn, which is much easier one. For example, 1 over n squared is much easier one, which we already know the convergence or divergence of the new series bn. Let's have a look at this one. Example 1. If you look at here, which series we are going to compare, we keep 2 to the n and 4 to the n, the highest power of the numerator and denominator. So this is our bn here. And let's have a look. Let's simplify a little bit. So it's 2 over 4 to the n, so which is 1/2 to the nth power. Or we can write it as 1 to the 2 to the nth power. So let's have a look at the limit. So first, an positive, bn positive. Second, we are going to take the limit an divided by bn. So limit and go to infinity. So it's 2 to the n times 2 to the n over 4 to the n minus 2. So this gives us 4 to the n over 4 to the n minus 2. As we know, as n go to infinity, we can ignore this number 2. So our limit will be 1. Because the limit goes to a number, that means our an and our bn, they have the same property. Based on our knowledge here, for bn, it's a geometric series with r equals 1/2 less than 1. So the series does converge. So as bn converges based on the limit comparison test, sigma n goes to infinity, an will also converge. Let's go over number 3. So if you look at this one, we keep the highest power, n squared, and n to the 5th. So that's our bn, which is 1 over n to the 3rd power. As we know, this series is a p series. P is equals 3 greater than 1. This series will also converge. So let's have a look. So an positive, bn positive. Second, we are going to take the limit and go to infinity, an over bn. When we do the ratio here, so this gives us n go to infinity. When you divide by bn, you multiply the inverse. So it's 2n squared minus 1 times n to the 3rd over 3n to the 5th plus 2n minus 2. Give us n go to infinity, 2n to the 5th minus n to the 3rd over. So as n go to infinity, we just need to look at the ratio of their coefficient, leading coefficient. So this gives us 2 over 3, which is a number. That means an and bn both converges or both diverges. Because we know n go to infinity, bn converges. So based on limit comparison test, that tells us n go to 1, an will also converge. So this is an, the other one is bn. So everybody, you can have a look at these problems and finish number 2 and number 4, 5, 6 and compare your answer with mine. Answer key for number 2. This is the answer key for number 4. 5 and 6.